Hi, in this video lecture I will discuss about the formation of p-n junction, that how it forms, and then after I will discuss the influence of external applied voltage on the p-n junction diode. Influence, when I am using this word, it means that biasing. When forward biasing and reverse biasing we use that, then what happens near about to the junction, or you can say variation into the depletion region. So first of all, the formation of p-n junction. Formation of p-n junction basically depends only one kind of wafers we use, and that is here p-type semiconductor material. And in that, basically what we do, we just drop the n-type semiconductor material or pentavalent impurity, you should say that. Then after some time what happens, that a part of this p-type vapor becomes the n-type semiconductor. So how it happens, basically that you can visualize by this way. I am adding pentavalent impurities into this p-type semiconductor vapors. This process carries on with very precautions, right, and it is done by this way. So I have just dropped pentavalent impurities into the p-type vapors, and in one part of that, or you can say one segment. So by this way you see here that left hand side is p-type semiconductor and right hand side is the n-type semiconductor. Now when it this process completes, then what happens, then that time basically two process carries on. One process is known as diffusion process, and second process is known as drift process. So diffusion process basically is because of the majority charge carrier. Here you see that this is n-type semiconductor, this one is the p-type semiconductor, and I have to discuss about the diffusion process and drift process, and on that basis what is the diffusion current and what is the drift current, right? So here what happens, as soon as you inserted the pentavalent impurity into the p-type semiconductor, then extra electron, free electron from the n side basically moves towards the p side, or you can say cross the junction, right? And as a result electron hole recombination take place, that is known as simply diffusion, right? Then other electron moves and fill the vacancy towards the p side, and again the electron hole recombination take place, and this is called diffusion, right? And similarly this is true for other electrons. And when the electron basically leaves the ion behind the semiconductor, n-type or p-type, here the electron basically, this electron leaves this ion behind it of it, and this ion is immobile, and this ion is of donor impurity. This is fixed with the other atoms of the lattice, so it cannot move here and there. So these atoms are basically fixed. So when electron leaves this n-type semiconductor material and reach towards the p, it basically leaves a ion, right? And these ions are immobiles. So by this way you see that near about to the junction there are no free charge carriers, and this region is known as depletion region. And here you see that the direction, because of these positive ions and negative ions, the direction basically of electric field which develop because of these is towards the p side. So electric field, internal electric field inside the p-type semiconductor will be towards the p, right? So this is about the diffusion current, diffusion current, is because of the majority charge carriers which moves from p-type semiconductor to the n-type semiconductor, and n-type semiconductor towards the p-type semiconductor. You know that in n-type semiconductor the majority charge carriers are electrons and minority charge carriers are holes, right? Similarly, towards the p side, majority charge carriers are holes and minority charge carriers are electron. So in the first section you have seen that a depletion region develops, and because of that an electric field basically directed from n side to the p side, and further because of this electric field what happens that these holes are basically attracted by the negative ions electric field, and as a result they starts to move. Initially what happens that diffusion current is large, because you know that there are majority charge carrier, and because of that obvious diffusion current will be large, and drift current is very small. But when this depletion region develops almost, then that time drift current starts to increase, right? And at a certain point what happens, this drift current becomes equal to the diffusion current, and then that time we say that there is no more flow of charge carrier from n side to the p side or p side to the n side, whether that is majority charge carriers or minority charge carriers. So here the point is related to the drift current. So drift current is because of the minority charge carriers, right? So now you have seen it, and these are flow of minority charge carriers from n side to the p side, and as a result of that you can observe the drift current. So drift current direction is from n side to the p side, and diffusion current is from p side to the n side, right? So electrons move from n side to the p side, majority charge carriers are electron towards the n side, so direction of the current will be from p side to n side. And because of the minority charge carriers are hole here, they move opposite to it, right? So the direction of the current will be like this, from n type to p type. So at a certain point what happens, this drift current becomes equal to the diffusion current, and then that time there is no more current. So this is the equilibrium condition in p-n junction diode. So you have seen here majority charge carrier, minority charge carrier, and movement of that across the junction, and as a result you have seen diffusion current and drift current, and here right now that is the equilibrium condition, right? In the next this section I am just summarizing that how electron diffuse into the p side, electron hole recombination, and as a result what happens, a depletion region develops. So this is our depletion region, and now the drift current is playing the role. So in this process basically what is happening, if you observe it carefully, that all these electrons from n side to n side are moving towards the p side by crossing this junction, and as a result the concentration of the charge carriers is increasing here. Which charge carrier? They are electrons are moving from n side to the p side. So you can say that concentration of the electrons are increasing towards the p, and you can see here the red dot indicate to the electrons, and this side towards the n side, these are in deficiency now. So because of this region, that potential basically change, and potential shape you can visualize by this way, that this slope which came through the depletion region is equivalent to this one. But the point is, the slope indicate the barrier height. This barrier height is denoted by V naught. It may be it is different for the silicon and of germanium, right? That you see here why the majority charge carrier cannot cross the junction after some time. That is the reason of this depletion region. That is the reason of the barrier height. Barrier height is equivalent to this one. You know that 0.2 volt is for the germanium and 0.7 volt for the silicon. So barrier height for the silicon is larger as compared to the silicon. So in case of these Y electrons, majority charge carrier from n side cannot cross the junction, that you can see here. The reason of that is this barrier height, right? So 0.2 volt for germanium and 0.7 volt for the silicon, and I have shown here this depletion region, p-type and n-type semiconductor, and the basic idea of that what happens after the formation of the junction, that p-type side becomes enriched by the electrons and it loses the electron from the n side, and because of that a new kind of situation develop that can you represent by this potential barrier. So now this is symbol of the p-n junction diode. You see here that p-type is shown by this triangle and this plate is shown by the n-type. Current flow from p side to the n side. Now in this section I will discuss about the biasing. There are two type of biasing. One is forward and second is reverse biasing. Forward biasing, when we define the forward biasing, it means that we are connecting the p type of terminal of the p-n junction diode with the positive terminal of the battery, and n type of semiconductor to the negative terminal of the battery. This is known simply as forward biasing, and if we reverse of it, then that will be the reverse biasing. It means if you connect n to the positive terminal of the battery and p type of the semiconductor to the negative terminal of the battery, then that time we say this is the reverse biasing. So in this section of biasing, what happens, what is more important point? So if you see in forward biasing, so forward biasing, the applied voltage mostly drop across the depletion region, right? How? That is shown by this picture. This is without biasing, the depletion region, right? And now you applied the biasing, and as a result you have seen that depletion region decreases. So I am connecting the circuit with the ammeter, voltmeter, rheostat and battery to show it more effectively. Voltmeter remains always parallel to the p-n junction diode, and ammeter is in series. Rheostat we use just to vary the resistance. So this is variable resistance. Ammeter which we have used here is in terms of the milliampere. The current is basically in milliampere, right? This is our battery. Battery means we are connecting to cells in series. Right, so by this way you can see it. Here the depletion region reduces because of the forward biasing, and this surface is the metallic contact, and that is connected to the voltmeter and rheostat by this way, and here p type is connected to the positive terminal of the battery. This is positive terminal of the battery, this is negative terminal of the battery. Negative terminal is connected by the ammeter with this n-type semiconductor. So this is circuit diagram for the p-n junction diode, and here you can see that depletion region is reduced. Now what happens? First point is this, that depletion region has been reduced in case of the forward biasing. Second point is what? Second point, if you see here that you connected this contact with the positive terminal of the battery, and because of that these holes basically push towards the n side, and here if you see these are the free electrons, and this is the negative terminal of the battery is connected with this metallic contact. It basically gives the force to these electrons to cross the junction, right? So these electron basically cross the junction and moves towards the p side. Here this hole basically moves towards the n side and cross the junction, but where the voltage drops here in this region. This is the depletion region. As I told earlier that this for the silicon it was 0.7 volt, and for the germanium it was 0.2 volt. So 0.7 voltage and 0.2 voltage drop basically here in this p-n junction diode before the current flow into the p-n junction diode, right? So for an example, if suppose you have 3 volt battery and you are using silicon, so then effective voltage will be 2.3 volt, which will be applicable to flow the current in this particular circuit, right? So you just reduce that voltage barrier height, and that appear into the VI characteristics of the p-n junction diode. When you plot it, you vary the resistance here, and when you will vary the resistance, it means the applied voltage will decrease or increase. So you can measure here in terms of the voltage, and then after you can measure the current in milliampere, right? Vary the voltage, observe the current, then again vary the resistance, right? Then read the voltage and current, and now plot it. This is again a proper symbol of the diode is used, as you have seen that this side where this strip is shown, that is the negative side, and rest of this part is positive side. So in the diode, so this is negative, so negative is connected with the negative of the battery, and positive is connected with the positive of the diode. This is the voltmeter across this p-n junction diode, that is parallel, and this voltmeter is in series. This is rheostat. So that earlier basically diagram is simplified here by using it. So now VI characteristics, you can see here that this is this red color ball basically is used to show the current, how it basically varies when you vary the voltage. On x-axis I have considered here voltage, and on y-axis I have considered the current in the unit of milliampere, and voltage in terms of the volt only. So let us see the behavior of the current in terms of this motion of the ball. So you see up to 0.6 it varies smoothly, and again of it varies basically sharply. So here you have seen that it follows this particular path, and again it increases rapidly. So till that, this is known as the cut-in voltage. Cut-in voltage is that voltage drop basically, which you have read into the earlier slide, right? So 0.7 volt, and beyond that the current basically increases. When you increase a small voltage, current increases sharply. So if suppose you have to find out the resistance of the p-n junction diode, that how much resistance it provide to for the current, then you can find out that resistance. But that resistance is not like that in ohmic resistance. This is non-ohmic devices, so the behavior is different. So that resistance is known as dynamic resistance, that is defined by the same way, delta V upon del I. For that purpose I use a linear portion of this VI characteristic graph, right? As you have seen that in ohmic basically devices, when you plot VI curve, that remains linear, like this line you have seen here at this particular slope, right? But in case of PN junction diode, when you will plot the VI, it basically comes into the exponential form like this. So for the slope, which section basically we choose linear segment of the graph for the slope always. So remember it. And because of that, dynamic resistance I have considered here is delta V upon delta I. Delta V means the potential difference between the 2 points. So V2 minus V1. So I have considered here this one is the V2 and this one is V1. Similarly, this is I2 and this one is I1. So delta V is equal to V2 minus V1 and delta I is equal to I2 minus I1. I am putting that value because I know that current is in milliampere, so I have converted that into ampere, and as a result, when I simplify this ratio, I found dynamic resistance in forward bias case, that is 1.42 ohm. Right, so this was the forward biasing of the PN junction diode and its characteristics. Let us see now for the reverse biasing of the PN junction diode. And here, as I told you earlier, that this is our n-type semiconductor, this is p-type semiconductor. We just reverse the direction of the battery. So this is positive terminal and this positive terminal is attached with the n-type semiconductor, and this is p-type semiconductor is connected with the positive terminal of the battery by this way. And let us see it properly through this circuit diagram. This is our PN junction diode, the direction of the positive and negative, our voltmeter and ammeter, this rheostat, and the two cells in terms of the battery. Right, so this is the circuit diagram of the PN junction diode, and we have to note down the readings. This is in unit of microampere. This ammeter scale is in microampere in reverse biasing case. So this is plus, this is minus, this is strip indicate to the plate, and that is negative sign, and negative terminal of this diode is connected to the positive of the battery, you can see here. Right, so now if you have to plot VI characteristics of the PN junction diode, then vary the resistance here and check the voltage, or note down the current reading, again vary the resistance, note down the voltage, note down the current, and by this way you can plot the VI characteristics. But what happens when you connect it? So this is suppose your depletion region without any biasing. Right now we are considering here reverse biasing. So this was the depletion region. What happens when we apply the reverse biasing? You know that depletion region increases here, right? So you have seen here that depletion region increased by this way. Now we will find out answer of it, that why the depletion region increases in reverse biasing and flow of current. So I am connecting ammeter, voltmeter, rheostat, and the battery. So this is our circuit diagram, and here you have seen that when we apply the reverse biasing, the depletion region increases and there is no current because of the majority charge carriers. The current in this case will be because of the minority charge carrier. You know that in n-type semiconductor the majority charge carriers are electron and minority charge carriers are holes. So that holes are shown by the these symbols, open circle. And in p-type semiconductor, you know the majority charge carriers are holes and minority charge carriers are electrons. So in this situation, when depletion region has been developed, you know that now, as in case of drift current, you know that minority charge carrier play the role. Similarly, same here, the minority charge carriers, these electron basically are attracted because of this field of these positive ions, and now these are basically will move towards it. Yeah, these are holes, right? So these holes will move toward this side. Let me see once again. This is the positive terminal on it, and the electron basically attract towards the metallic contact, and this metallic contact will give the force to these holes, and force to these holes, and these holes will cross the junction towards this side, right? And similarly, from this metallic contact, the minor this is the negative, it is connected with the negative terminal of the battery by this way, and this negative electrode basically will give the force to these electron to cross the junction, right, by this way. So electron will move right into this direction, hole will move into this particular direction. So this is the very small current, and because of that we measure it into the microampere, right? So in case of reverse biasing, current is small, and where it is independent from the potential. If you vary the resistance here and note down the potential, and further you will notice that there is no change into the current, but at a certain value of the potential you will notice that current abruptly change. The reason of that, because the bonds basically break down of the device, and sometimes it basically burns if you reach beyond that limit. So here you can see that this is the voltage scale, and this one is the reverse biasing current, reverse bias voltage, right? So that is shown by this way, and this blue color line indicate that if you are increasing the voltage, right, there is no change into the current. So this is saturation current, but at a critical value of the voltage it basically rises sharply, but that is also in terms of the microampere by this way, right? So here in case of reverse bias, suppose I have to find out the resistance of the PN junction diode, that how much basically it gives the resistance to the current. So for that I have to measure the dynamic resistance of the diode, that is calculated by the same way as in case forward bias. So I am taking the linear portion of this graph, right? So we consider always the linear section of the graph when we have to take the slope. So this section, so this current is in microampere, and this voltage in unit of volt, right? So the difference V2 minus V1, I2 minus I1, and that is of the order of 10 raised power minus 6 ampere. I have converted here microampere into the ampere, and as a result when I solve it, I found that the dynamic resistance is in terms of 10 raised power 6 ohm, that is mega ohm. So you can realize that how much resistance basically diode provide to the current in reverse biasing. It means current cannot flow into the reverse biasing, right? So that is shown by this picture, that this symbol I am summarizing here. This was the circuit diagram for the PN junction diode, depletion region and notation of it, N type and P type, and the current basically flows only in one direction. This is the positive point of the PN junction diode. Battery, emitter, voltmeter, rheostat I have used, resistance, right? And I want to focus only one thing here again, because if you know that you can understand easily all the electronic devices if you know about it. And that is the symbolization of the p-type and n-type semiconductor structure. Here in my explanation I have used this circle and notation and a dot or open circle. So this is the n-type semiconductor I have considered here. So there basically this positive sign indicate the donor impurity, and donor impurity have one electron. That electron is associated with it, that is shown by this red color dot. So this is the proper notation. And here this positive ion is of the donor impurity. When electron moves from n side to the p side, it basically leaves behind these immobile ions near about the junction. Right, this is the p-type semiconductor. Here you see that this negative ion basically is of the acceptor impurity, and you know that have one vacancy and one hole basically that you represent it. So hole is associated with the acceptor impurity. If you use this symbolization for the p-type and n-type semiconductor, then there is no problem to understand the electronic device is working. And semiconductor p-n junction diode semiconductor device is the basic fundamental device. If you know the working of it, then you will not face even a single problem in explanation of the transistor or any other devices which is based on it. So application of the p-n junction diode is so large. You can see here that signal diode, light emitting diode, IR, LEDs, photodiodes. They are so large application of the p-n junction diode. You can see here in laser diodes we use it. So I hope I have make it clear. If this lecture is helpful to you, then please like and subscribe the video for latest and upcoming video. For more information about this lecture you can find out at apniphysics.com. Thanks for watching. If you have any doubt or any question, you can message me just below this video. Thanks.